In this video, we will talk about log properties and the chain rule. So I want to begin by giving a proof of why the derivative of ln of x is equal to 1 over x. All right, so here's how I'm going to do this. So let's give a proof. So I'm just going to write PF to abbreviate proof. Okay, so that indicates to my reader that, oh, I am about to start my proof. All right, so the idea behind my proof is, so we know that if we take f of f inverse of x, that just equals x. So we can sort of think of this as the inverse function and the original function f. They sort of undo each other. So when we plug x into it, you do f inverse, you apply f inverse to it, that gives us something. And then applying f to that result will sort of undo that operation and then give us back x, the thing that we started with. So algebraically, the reason why this is true is if f of a is equal to x, well, that's equivalent to saying that f inverse, when we write f inverse, it's got to switch the role of the input and the output. So x will now be the input and a will be the output. Okay, so we are saying that f inverse of x equals some number a. Alrighty, so then let's look at f of f inverse of x and what that equals. So this is f of f inverse of x, but we're saying that f inverse of x is this value a. Okay, so f of f inverse of x is just f of a, but what's f of a? F of a was x. So what we've just shown is, we've just shown that f of f inverse of x equals x. Okay, so I'm going to put this in a thought bubble. Put this in a little thought bubble, so that's where this comes from. This is a property that you likely would have seen back in algebra. All right, so I'm going to apply this by letting my function f of x be e to the x. And in that case, the inverse function, the inverse of e to the x is ln of x, the natural log of x. Okay. So if I plug in f inverse of x into f of x, where the x is, we will get e to the, and now I plug in ln of x for the x, e to the ln of x. And this is supposed to be equal to just x. That's what I have on the right-hand side when I do this. Okay, so e to the ln of x is equal to x. So now let's differentiate. That just means take the derivative of. Differentiate both sides. All right, so we will take d dx, the derivative of e to the ln of x, the derivative of the left-hand side, and we'll take the derivative of the right-hand side. So if those two sides are the same, then their derivatives should also be the same. Okay, so when we take the derivative of the left, let's do a little bit of review now. This is some chain rule review. Just like even in the last video, we did some chain rule review. So when we take the derivative of e to the stuff, we need the chain rule. In fact, let me give myself some more room here. The derivative of e to the stuff is, first you take the derivative of the outside portion. The outside function in e to the stuff is actually e to the x. So we'd write e to the, but instead of writing e to the x, the chain rule says keep plugging the same inside thing in. And the inside function is the stuff. So it's e to the stuff. And then we multiply by the derivative of the stuff. So the derivative of the stuff. Okay, I'm running out of room, so I'm going to shift this over. All right, so this is something that we've seen before. The derivative of e to the stuff is equal to e to the stuff times the derivative of the inside, which was the stuff. If you have questions about how we're getting this or how we got it before, please ask those questions, because I want to make sure that this makes sense. Alrighty, so now let's take the derivative of the left-hand side using that chain rule. If we do that, we'll get e to the stuff, which is e to the ln of x, times the derivative of the stuff. So the derivative of ln of x, and this equals the derivative of the right. The derivative of x is just 1. Okay, so we are trying to figure out what the derivative of ln of x is in this process. And now it's shown up. All right, so we have this e to the ln of x. But remember, we know what that is. We know that e to the ln of x equals x. So that equals x. So now let's just divide that over to the right-hand side. And if we do that, we get the derivative of ln of x equals 1 over x. And that has proved it. Okay, so there's a symbol that we write in math when we're done with proofs. And that symbol, it depends on either the textbook that you're reading or who's showing it to you and what they've learned or what their preference is. But the symbol that I like to use is I draw a square and I shade it in. This is very commonly used. So this is a symbol for done with proof. We are done with this proof. We've actually proved why the derivative of ln of x equals 1 over x. It involved the chain rule. All right, so let's do an example now. Okay, so we're switching gears a little bit. We started off with a very theoretical thing, but now we're going to go into an example. So we have this function f of x, and I want to find f prime of x. So I'm going to talk about this in 2 ways. So method 1, when we see ln of some stuff like this, is to just go at it with chain rule right away. Go at it with chain rule right away. So let's look at what would happen if we did that. We would get f prime of x equals, so the derivative of ln of some stuff is, well, the outside function is the ln portion, ln of x. And taking the derivative of that, we'd get 1 over, typically we just write x. But when we do the chain rule, we keep writing the same inside thing in when we do the derivative of the outside portion. So we'll have 1 over 5x plus 2 to the 4 times 2 minus x to the 11 times e to the 2x plus 1. So it's 1 over the stuff times the derivative of the stuff. So we'd have times the derivative of that stuff, the 5x plus 2 to the 4 times 2 minus x to the 11 times e to the 2x plus 1. So we'd have this. All right, so that's how we take the derivative of ln of stuff using the chain rule. But now we got to do the derivative of all of this inside stuff. And to do the derivative of this, we have 3 functions sort of multiplying each other. And we've done an example like that before, back in product rule. This involves using the product rule twice, which we can do. It's just a bit tedious to do that. So it's definitely doable. It's just a little tedious. So let's talk about another way that we could approach this, which is more efficient. So method 2 for doing this is we can actually use log properties to simplify our function first. So what if we use log properties first? So for example, when we have ln of something times something times something, that's ln of the first thing plus ln of the second thing plus ln of the third thing. So that's one of our log properties. Okay. So now we can use another log property. Ooh, let's write f of x. All right. So when we have a power inside of the log, so because this 4 is the power of everything inside of the log, we can move it to the front. So we get 4 times ln of 5x plus 2. Do the same thing with the 11. We'll get 11 times ln of 2 minus x. I cannot do it with this last log because 2x is not the power of everything inside of this ln. So I have to leave this last one as ln of e to the 2x plus 1. All right, so now let's take the derivative. So taking the derivative of this, now these ln's are a lot simpler to take the derivative of. Okay, so the 4 is a constant multiplying this. That's going to stay there. And then the derivative ln of stuff is it's 1 over the stuff So the stuff is going to come to the bottom. And then we multiply that by the derivative of the stuff. So we multiply by the derivative of the stuff inside. I'm going to now start to go a little bit more quickly with these examples. So instead of writing like ddx of that stuff every single time, I'm just going to start to say what the derivative of that stuff is. In this case, it's 5. Okay. So I want you to know how to do it the long way, where I keep writing ddx of the stuff and really show all the steps and then evaluate the derivatives, which is how we've done it up until this point. But now that we've done a bunch of examples, I'm going to start to go more quickly through some of them. Okay, so next term. We have this 11, which stays there because it's multiplying my ln, and it's a constant. And ln of 2 minus x, the derivative of ln of stuff is 1 over the stuff. So we get 11 over 2 minus x. And then we multiply that by the derivative of the inside stuff, which is negative 1. All right, let's do the same thing for this last ln. We're going to get 1 over the stuff, 1 over e to the 2x plus 1. But we have to multiply that by the derivative of this stuff inside. And the derivative of e to the 2x, that requires chain rule again. Another chain rule. Another chain rule here. The derivative of e to the 2x is, so that's e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of what's inside times the derivative of the stuff. And the derivative of the stuff, the 2x, is 2. Okay, so that's the derivative of e to the 2x. It's e to the 2x times 2. And then plus the derivative of 1 is 0, because that's just a constant. And at this point, we have finished taking our derivative. So this would be our answer. If I did need to simplify it a little bit, I could. Like 4 times 5 is 20. 20 over 5x plus 2. Negative 1 times 11 will give me negative 11 over 2 minus x. And then this last fraction I could write as 2e to the 2x over e to the 2x plus 1. Maybe if I wanted to clean it up a little bit. All right, in terms of our goals, we have done goal 3. We've proved why the derivative ln of x is 1 over x. And we've done an example using log properties to take derivatives. So we're continuing to sort of increase the level of difficulty that we're looking at with these examples. In the next video, we will do an application of the chain rule to a cost revenue profit problem.